given our correct assumptions, right? And it's not written in here, maybe it should be, right? We need to make sure we have an appropriate sample. Always number one. Then number two, we always check our mathematical assumptions. That's that first clause, right? Our mathematical assumptions here are going to be the exact same as our mathematical assumptions were in chapter 7. We go through that gated approach. If x is normally distributed, then x bar is normally distributed. Boom, we're good to go. If not, we call on the central limit theorem. Central limit theorem says that as my sample size is bigger, the distribution of x bar becomes more normally distributed, so I need a large enough sample size to overcome any skewness of x. Right? If we don't know anything on skewness, we say 30 is large enough. If we have a skew distribution, we need even more than that. If we have symmetry in our distribution, we don't even need that many, right? So the same things we talked about in chapter 7, right? And again, why is that? It's the same reason for proportion problems, right? In the proportion problems, we built everything around p hat, so we had to show p hat was normal, so we checked the same stuff we did in chapter 7 for that. Here, same thing, we're going to build this interval around x bar, and so we need to make sure x bar is normal, just like we did in chapter 7. So same assumptions that we had in those problems, and there's your confidence interval. Just as we've said hundreds of times already, a confidence interval is built by a point estimate plus and minus a margin of error, where a margin of error is equal to a critical value times a standard deviation. We start with our point estimate right here, x bar. It's our point estimate from u. We're going to add and subtract. Subtraction gives us our lower bound. Adding gives us our upper bound. A critical value, we can't use a z. We have to use a t. Why is that? Because we like to take the standard deviation of a mean problem, which was sigma over square root of n. But remember, we're oftentimes not going to know sigma. So if we don't, like we talked about, if we don't know sigma, what do? We estimate it with s. When we use s, we have to use t. We use degrees of freedom to equal to n minus 1. And then this part, again, should look relatively familiar. We just swapped out sigma and swapped in s. And so let's see how this would work. In an effort to control heating costs, suppose we are considering charging a fee if the average thermostat is set above 72 for the entire dorm. So we're going to take a sample. We sample 35 rooms on our floor and find the average thermostat at 73 degrees with a standard deviation of 4 degrees. So make sure that we're understanding the difference between x bar and the value in the claim. It's the same thing that we talked about with proportion problems. Same thing here. We have to figure out which one's x bar and which value is the one that's about the claim that we're going to be assessing in the problem as well, right? All these problems are going to be 3 parts, right? They're going to be find the confidence interval, address some claim, and then talk about your assumptions, right? So what's the value that goes for the claim and what's the x bar, right? So just be comfortable with how these problems can be worded. X bar is going to be where was the sample, right? The sample was 35 rooms. That's my n, and we found an average of this, so that's my sample mean 73 degrees. The 72 is about the claim, so we'll come back to that later. Has no bearing on the actual interval. And a standard deviation of 4 degrees. How do I know that this is S or sigma? Okay, and this is where we just stop, and now we have to recall on our English skills and our comprehension there. We take a sample of 35 rooms, and so because we take a sample, until we hear otherwise, the things that follow this in the sentence are all referring to the sample. We take a sample of 35 rooms and find, boom, x bar, because average from samples x bar, and we find this. So just ignore this clause. We take a sample of 35 rooms and find a standard deviation of 4 degrees. Boom, sample standard deviation right here. Right, if it's population standard deviation, it would say we take a sample of 35 rooms and find an average thermostat set to 73 degrees with a known population standard deviation of 4 degrees, or even just a known standard deviation, right? Because known is one of those population words, right? Or with a true standard deviation, right? So one of those population words pops in there. You say, oh, that's sigma, right? But in this case, it doesn't. It just adds on to the clause before it. So that's going to go back to the sample, which we set out here from the start of the sentence. That's the sample standard deviation, so that's S. All right, so I'm just going to write down my statistics from the problem right off the bat. X bar is 73, S is 4. That X bar is important, of course, because that is the point estimate that we're going to center the interval around. S will be used in the margin of error. How do we find a margin of error? Again, a critical value times the standard deviation. And now we just got to plug in. Again, as before, remember, don't plug in we have a 5% significance level. Don't plug in 0.05 for t. Don't plug, that's 95% confidence, right? Don't plug in 0.95 for t, right? Make sure we go to our t table and plug in the correct critical value. We know that n is 35, which means we have 34 degrees of freedom. So we're going to look at that row, and 95% confidence gets us a critical value of 2.032. Plug in the other two numbers. and then you can get your margin of error. Again, take that margin of error, subtract it from your point estimate to get the lower bound, add it to it to get the upper bound, and you should be able to arrive at this interval. And then we got to write our sentence, right? We are 95% confident that the interval from 71.63 degrees to 74.37 degrees contains the, and just like before, 3 key pieces. You need to have some parameter piece, right? Tell me true, known, actual, real population, some parameter word. And why is that important? Because I want to make sure that we don't lose sight of what we're doing, right? And writing these sentences the whole point of this is I've got this range of values and I think the parameter's in there. Notice what I said, the parameter. So I need some word that tells me that you think the parameter's in there, not the statistic. Because I don't have to have a confidence interval on a statistic. I know what the statistic is. The statistic is literally 73. There's no guessing on that one, right? The confidence interval is this range of values that I think has the parameters. Tell me a parameter word. So contains the population, true, whatever, right? Just as before, whatever metric you're using, you can use average and mean interchangeably. And then context of the problem, thermostat settings of the rooms in this dorm. Now again, the order of addressing the claim and the assumptions doesn't really matter. This problem has the assumptions next. We can do the claim next, it doesn't matter. Remember, number one, we're always going to be talking about our sampling methodology. Okay, do we have any sampling bias, response bias, non-response bias? And on this problem, I would say we might have a bit of sampling bias because we only sample rooms on our floor and not the whole building, right? A good representative sample would be sampling people on every floor, right? We don't know about people living in the basement, people living on the top floor. Wherever you live might actually affect what the thermostat is set on. It may not, right? And that's the whole point with sampling bias, is that it may affect the results, it may not. We just don't know. And so it's just something we have to call out and kind of say, a little bit of caution, this might mess up our results, but our results may be totally fine. We don't really know, right? And so I'm going to say number one, we can only draw conclusions on the floor from which we sample instead of the whole building. So you got two options, either A, you say we might have a little bit of sampling bias, or B, you can say we're 95% confident that the interval from 71.63 to 74.37 contains the true average thermostat setting in the rooms on the floor that I live in this dorm, which is less helpful because the fee is going to apply to the average of the dorm, not just your floor, right? So it's kind of a rock and a hard place right there. Either A, we just have to say if we're trying to make inferences on the whole floor, there might be a little bit of sampling bias, or you might say I really can only make inferences on my floor and I don't really know what all the other floors are doing. Number two, then we come back and check our mathematical assumptions. Again, just as a reminder for our proportion problems, that was we have to make sure all three hold x is binomial n times, or excuse me, we have 5 successes and then we have 5 failures. For this problem, it's that gated approach, just like the ones in chapter 7. We're going to first start off and say if if x is normally distributed, then x bar is. If not, then we check central limit theorem. Notice in this problem, we have no idea what the distribution of x is. There's nothing in there about symmetry, skewness, normality, nothing. So because we know nothing about the skewness, we're just going to talk about our sample size, and I'm going to say 35 is greater than 30, and so I can say x bar is approximately normal. And as we've talked about before, never a bad idea to come back and make some concluding statements. Are the results valid? Are the results not valid? I'm going to summarize them and say everything's fine, except we have to make sure we can only make inferences on our floor. And the last piece, address your fear that you might soon be paying more money. Well, notice there's no number in that claim, but we can link that back to the problem. The problem says we're going to pay more money if the average is above 72. And so just as before, we have to say, does the entire interval sit above 72 degrees? If the entire interval does, you can say, yeah, I'm confident I'm going to be paying more money. If some of the values are and some aren't, you say, maybe I'm in, maybe I'm not. I can't conclude that. It's possible, but I don't really know. Right? But notice this, there are some values below 72, right? The truth could be anywhere in the interval, and the truth could be 74, and the truth could be 73, and the truth could be 72.1, but the truth could be 71.7 or 71.8, right? And that would not be above 72. So I would say I cannot conclude the average thermostat is set above 72 based on the interval. And I know it's possible, right? Again, it's that always, sometimes, never true, right? Is the interval always agreeing with the claim? Is it sometimes agreeing with the claim? Is it never agreeing with the claim? Here it sometimes agrees, and so we would say it's possible, but I can't conclude it. I can't firmly say, yes, the entire interval agrees with that. But I also want to make sure we know incorrect sampling methodologies should give us a little bit of pause, right? Maybe if we sampled better, maybe the interval would look a little different, and maybe that lower limit would go above 72, and maybe that would change my decision, right? And that's the issue with bad sampling, is that we say it could affect our results, right? Our results here, I would say I cannot conclude I'm going to pay more money, but maybe with better sampling, maybe that would tell me I would be paying more money, right? Let's move forward to the next example. As before, if you want to pause here and see if you can work through this problem on your own, not a bad idea. If you're still a little bit lost, work through it with me either way. Make sure we're getting enough practice through these problems in the notes, problems in the homework. Dallas Stars hockey team has 24 players on it, and the average player weight is 200.2, while the standard deviation is 18.2. Same thing as before. It's one clause. Here's a sample with 24 players, and so that's the X bar because it's from the sample. That's S because it's from the sample, right? Either one of those is mu or sigma. Knowing the data appears to be somewhat symmetric and treating the stars as a representative sample of hockey players, construct a 95% confidence interval on the average weight of all hockey players. So I'm going to write down my statistics, X bar and S, just like before. I'm going to find my margin of error. Degrees of freedom would be 23. That's where we got that 2.069 from the appropriate row of the t-table. Add and subtract that to your point estimate, and we can get our interval. As such, then we just have to write our sentence. So we're 95% confidence that that interval contains. Notice here what I did. I did a little switcheroo, right? Notice I didn't put the parameter word first. I put it here, right? Doesn't matter where it goes, as long as it goes somewhere in there, as long as it makes sense from an English standpoint. It contains the average. That's the metric we're using. Weight of hockey players. That's the context. And then all. There's my parameter word right there. So you can kind of put it in a couple different places, just as long as it's there and makes sense from an English standpoint. Just to claim that the mean weight of all hockey players is over 195 pounds. And so if the entire interval is over 195 pounds, we would say, yes, we can agree with this claim. If it's not, we would say we can't. And so in this case, there are values less than that. So I'd say because 195 lies inside the interval, we cannot conclude the mean weight is over 195 pounds. We can say it's possible. This is a sometimes. Some of the values in the interval agree with that. Some don't. So possible but cannot conclude. And then for our assumptions, again, first we're checking our sampling methodology. You might start off and say, wait a minute, is this one team? Is this good sampling? Is this representative? But notice what I did in the problem. Notice, because I would start off and I would say, maybe this team is representative of all the teams, maybe not. Maybe they're a younger team, maybe they're an older team, maybe they're a faster team, maybe they're a more physical team, right? All these different things that might matter. But notice at the top of the page, we said, knowing that the data appears to be somewhat symmetric and treating the stars as a representative sample of hockey players. So from the start, basically someone with expert knowledge has come in and said, you are allowed to treat this as representative. And that's what happens with these sampling biases, right? It's left up to the expert to say what you can and can't do. And so in this case, it's we just want to call out, right, and let someone else make that decision. And maybe one day you'd be that person who'd be talking to a statistician and you would make that decision, right? So if that sentence wasn't there, I would say we might have some sampling biases, might cause some concern, but basically in the problem we've preemptively said, hey, the experts come in and the expert says you can treat this as representative. I don't think that's a problem. Right, but our job is to call it out and to say if it's a problem or not. In this case, the problem already goes ahead and say, hey, don't worry about it. We got you covered here. So I'm going to say because we are allowed to treat this team as representative, we're good on our sampling. We've already been given a pass there. Okay. Then we check our mathematical assumptions. We don't know if X is normally distributed. It's always nice if the problem tells us that, or if we had a picture for that. And we have a small sample size, right? It's less than 30, but notice again at the start of the problem, it says knowing the data appears to be somewhat symmetric. And remember, we said that if we had symmetry, we didn't need a sample size of 30, that a sample size even a little bit less would be fine. So because we're close to 30 with that symmetry, we can go ahead and say that X bar is approximately normal, and thus, concluding all of that, our results should be accurate.